Hello everyone, welcome to the fourth video of concrete technology. In today's video we are going to discuss the different testing methods, physical testing methods of cement, and along with that we will also discuss the water cement ratio and what are the effects of water cement ratio on the strength of concrete, and then we will discuss workability. So let's start with the physical tests for cement. Uh, Actually, we have 5 different tests to check the fineness of cement, soundness of cement, consistency of cement, initial and final setting time of cement, and then compressive strength of the cement. So let's start with the first test, which is called fineness of cement test. As its name is showing that this test is performed to check out the fineness of the cement. So the fineness test of cement is made by sieving it through sieve number 9. We will do sieve analysis and pass the cement through sieve number 9. So the residue retained should not exceed the following limits. The limits are that if the cement is ordinary Portland cement OPC, then the residue should be 10%. The residue which is retained on the, let me show you an image. Let me bring it to forward. So these are the different components or apparatuses which we are using for the fineness test of concrete. Cement sieve lead, 90 micron sieve, which is sieve number 9, and then weighing device and sieve shaking machine, right? So the fineness test of cement is made by sieving it through 90 micron sieve, or this is also called number 9 sieve. We will pass cement through it. So the residue which is retained on this sieve number 9 should not be more than 10% if the cement is ordinary Portland cement, and it should not be more than 5% if the cement is rapid hardening cement, and it should not be 5% if the cement is low heat cement. So the retention of residue on this sieve number 9 will be different for different kind of cements. As I said that for OPC it should be 10%, the retained residue should be 10%. For rapid hardening and low heat cement it should be 5%. So this is the method or test which we use to find the fineness of a cement. So the next test we perform for cement is to check the soundness of the cement. For the soundness of the cement, bring it to front. Okay, this is the device which we use for soundness test of cement. I think there is no need to go into the depth and details of the apparatus and how it performs. We just need to remember the name. Lichetier's apparatus. Lichetier's apparatus is the device or apparatus which we use to find the soundness test of a cement. A sound cement should not experience any appreciable change in volume after it has set. If there is no appreciable change in the volume, then we can call that cement a sound cement, right? So this is one of the property. So the volumetric change occurs if excess free lime and magnesia are there in cement. When will volumetric change will occur? Volumetric change will occur if there is free lime and magnesia are there in the cement. Soundness test is performed to discover this effect in a short time. So the apparatus used to perform the soundness test is Leichetier's apparatus. Right? This is the device we use for soundness test of cement. And the next is consistency and initial and final setting time. For these both tests, we use same apparatus, which is called Vickers apparatus. For consistency and initial and final setting of the cement, we use Vickers apparatus. Let me show you Vickers apparatus. Bring it to front and then enlarge the image. So this is what we called Vickers apparatus. This apparatus is used to find the consistency as well as the initial and final setting time of cement, right? So consistency test of cement. This test is performed to determine the quantity of water required to produce a cement paste of standard or normal consistency. Actually, the quantity of water depends a lot and it affects the strength of the concrete. So it is important to find out the right quantity of water for any concrete, or if you are making a cement paste, it is important to find out the right quantity of water required. So to find out the quantity of water required to produce a cement paste, we actually perform this test by using Vickers apparatus. So standard consistency of cement paste may be defined as the consistency which permits the, this is called Vickers plunger, right? So the consistency which permits the Vickers plunger to penetrate to a point of 5 mm to 7 mm from the bottom. This is the plunger which should penetrate 5 mm to 7 mm from the bottom of the Vickers mold. When the cement paste is tested within the gauging time 3 to 5 minutes after the cement is thoroughly mixed with water. So this is the process. Actually, there is no need to remember the process or all the procedure of the experiment. We just need to remember the device which we are using to find the consistency of a cement or initial and final setting time of cement. That is called Vickers apparatus, and these are different components. So for setting time also we use this apparatus. The in cement hardening process, two instants are very important, right? The initial setting and the final setting time. So the initial setting time, the period elapsing between time when water is added to the cement and the time at which the needle 1 millimeter square or 1.13 mm dia, 50 mm in length, falls to pierce the test block by about 5 mm is known as initial setting time of cement. Actually, again, this is related to Vickers apparatus. We perform this experiment in Vickers apparatus to find out the initial setting time. Then we do the experiment for final setting time too in this same apparatus. The final setting time is the period elapsing between the time when water is added to the cement and the time at which a needle used for testing final setting upon applying gently to the surface of the test block makes an impression while the attachment of the needle fails to do so is known as final setting time of the sample cement. So for finding the initial setting time and final setting time, Vicart apparatus is used. So in this, I think we just need to remember the definition of initial setting time and then final setting time, and the device which we are using to find the final and initial setting time, and the different components of this device. So I think that's fine, because we are preparing for the multiple choice questions related to concrete technology, so there is no need to go in depth about the experimental procedure. So the next test we perform for the cement is compressive strength test. This test is performed to find out the compressive strength of the cement, right? So this is the device which we use to find out the compressive strength of cement. So as you can see in this image, this is the machine or the device which we are using. This is called compressive strength testing machine, CTM, right? This test is very important. Actually, among all these tests, compressive strength test is important one. This test is in this test we actually made 3 molds, as we can see in MH2. One is here in the compressive test machine, and 2 are here. So we make 3 molds, and the face area of each mold is 50 centimeters square, and these are prepared and cured under standard temperature conditions, and each cube is tested by placing it between the movable jaws of compressive strength testing machine. So the rate increasing load is 0 in the beginning and varies at 350 kg per centimeter per minute. So after every minute we will increase the load at the rate of 350 kg per centimeter square. So the load at which the cube gets fractured divided by the cross-sectional area of cube. So the point at which the cube gets fractured, we will note the value we get. That will be the compressive strength of that cube, and we will do the same procedure for the remaining 2 cubes too, and we will note all those 3 values of compressive strengths, and then finally we will take an average of the compressive strengths of those 3 cubes, and that average will be the compressive strength of that concrete mix or concrete paste. So this is the compressive strength test. These were 5 different tests. These are called physical tests of cement. So the next is water cement ratio. So the ratio of water and cement by weight in a concrete mix is known as the water cement ratio. Water and cement, the ratio of water and cement between the weight of water to the weight of cement used in the concrete mix is called water cement ratio. Actually, this is very important, water cement ratio. Water cement ratio of 0.4 to 0.6 are more typically used. For higher strength concrete, lower ratio are used along with a plasticizer to increase the flowability of the concrete. Too much water will result in segregation of sand and aggregate components from the cement paste. So this is showing that if the water cement ratio is higher, then what will be the results? The results will be segregation of sand and aggregate components from the cement paste. Sand and aggregates will segregate if we use too much water. Too much water means high water cement ratio. So the another thing is that for higher strength concrete, low ratios are used. So if we are looking to get high strength concrete, we will obviously keep the water cement ratio low, because lower ratios have higher strength of concrete. So this means that water cement ratio and the strength of concrete are inversely proportional. So the lower water cement ratio, higher will be the strength of concrete. If the ratio is higher, the strength of concrete will decrease. So these are important points which we need to remember. Let me share this table. Actually, this table is showing the minimum cement content and then maximum water cement ratio and minimum grade of concrete for different exposures with normal weight aggregate of 20 mm nominal maximum size. So this table is actually showing the relationship between different types of grades of concrete, and then what sort of water cement ratio we should maintain for plain concretes and reinforced concrete. So let me take an example, like if the minimum grade of concrete is M15, as in M15 this side 15 is showing the compressive strength and M means mix, right? So 15 is the compressive strength after 28 days. This 20, this is 20, this is 25. So these numbers are showing the compressive strength of the concrete after 28 days, and M shows the mix. So as we can see that as the compressive strength of concrete is increasing, here the water cement ratio is decreasing. Got it? As I said earlier that water cement ratio and compressive strength of concrete are inversely proportional. As the compressive strength is increasing from 15, 20 and then 25, the water cement ratio is decreasing from 0.6 to 0.5 and then 0.45 and 0.40. Similarly, in this case too, in reinforced concrete too, as the compressive strength of concrete is increasing, water cement ratio is decreasing. So the important point is that we need to remember that the water cement ratio decreases with the increase in the compressive strength, or or we can say in other words that with the increase in the compressive strength of concrete, the water cement ratio decreases. So both are inversely proportional. So let's see the effect of water cement ratio on strength of concrete. As we previously discussed, that is the same thing. Actually, according to the water cement ratio law, the strength of concrete only depends upon the quantity of water used in workable concrete mix and is quite independent of the proportion of cement and aggregate. Actually, there is a law which we call water cement law, water cement ratio law, which was introduced by Ibrahim in 1918. That law says that with given concrete material and conditions of test, the quantity of mixing water used per bag of cement determines the strength of concrete, so long as the mix is of workable plasticity. So according to this law, the main theme is that the strength of the concrete actually depends upon the quantity of water which we are using per bag of cement. So the strength of concrete is inversely proportional to the water cement ratio, as we already discussed. That is, lower the water cement ratio, greater is the strength of concrete, and vice versa. So the relationship between water cement ratio by weight and the developed compressive strength of concrete at 28 days may be shown in this graph. As I have shared this graph, when water cement ratio becomes less than 0.4, whenever water cement ratio becomes less than 0.4, the compressive strength will increase, but it also indicates that the concrete is not workable. It will remain not workable because the definition of workability is that the ease with which the concrete will easily flow, right? So whenever water cement ratio will decrease, the workability of concrete will also decrease. So there are two relations actually. Workability and strength of concrete are inversely proportional, but the water cement ratio, sorry, let me repeat it again. There are two relations, right? The first relation is that water cement ratio and compressive strength are inversely proportional. Inversely, right? And water cement ratio and workability are directly proportional, because whenever water cement ratio decreases, then the workability of concrete will also decrease. So what will happen if workability decreases? If the workability decreases, then if such a concrete is used which has low workability, then we can expect honeycombing structures, right? If the workability is less, then honeycombing can occur in the concrete. So these are some of effects of water cement ratio on the strength of concrete. The next is factors. There are various factors which can affect the workability of a concrete. So some of the important factors which are affecting the workability of concrete are water content, size of aggregate, shape, shape of aggregate and surface texture, porosity and absorption, grading of aggregate, and then temperature. So let's see the first factor, water content. We will see each factor, either they are directly proportional to workability or inversely proportional to the workability. So the first factor is water content. Workability of concrete mix largely depends upon its water content, right? It increases with increase in the water content on account of greater lubrication. So as we said in the previous slide that there are two relationships, right? The water cement ratio and compressive strength are inversely proportional, but water cement ratio and workability are directly proportional. So water content or water cement ratio, if it increases, then the workability will increase because both are directly proportional. And then the size of aggregate. Concrete having large size aggregates is more workable than the containing small size aggregate. This is due to the fact that smaller size aggregates offer greater surface area than that of the larger size aggregates, and thus more water is required to lubricate the small size aggregate. So size of aggregate is again directly proportional to the workability. If the size of aggregate is more, then concrete will be more workable. Next is shape of aggregate. There are various shapes of aggregate like angular aggregates, flaky aggregates, elongated aggregates. So the angular aggregates, flaky aggregates, and elongated aggregates reduce workability. On the other hand, the round aggregates increase the workability. So there are two cases when we come to the shape of aggregates. Round shape aggregates are directly proportional to workability. So whenever there are round shape aggregates, the workability of the concrete will increase, right? If the aggregates are of round shape, then the workability will increase. However, on the other side, if the aggregates are angular shaped, flaky shaped, or elongated shaped, then the workability will reduce. So the next factor is surface texture. Surface texture also affects the workability of the concrete. So the rough surface aggregates need more water for lubrication. Obviously, because they are rough, they will need more water for lubrication and thus reduces the workability. Smooth surface aggregates require less amount of water for lubrication and hence increases the workability. So again, the relationship is that smooth surface texture, if the surface texture is smooth, it will increase the workability. If the surface texture of aggregates of aggregates is rough, right, then the workability will decrease. So next point is porosity and absorption of aggregates. What is the effect of porosity and absorption of aggregates on the workability of concrete? A porous and dry aggregate requires more water, right? If the aggregate is porous and dry, then it requires more water for lubrication as compared to a non-porous and saturated aggregate. In porous and dry aggregates, a portion of water added to concrete mix is consumed to fill the pores and thus workability is reduced. Right? If it is porous, then it will reduce the workability. If it's non-porous or saturated aggregates, then it will increase the workability. Next is grading of aggregate. The grading of aggregates affects the workability of lean concrete mix. It also only affects the lean concrete mix. The next is temperature. At higher temperature, workability of concrete mix is reduced. So temperature and workability are actually inversely proportional. If the temperature is increased, at higher temperature, the workability of the concrete mix will decrease. So these are different factors and their effects on the workability of the concrete. The next is method of determining the workability of concrete, which we will discuss in the next video. So for today, that's it. So in the next video, we will discuss the methods of determining the workability of concrete, different methods we are following, and then good quality of an ideal aggregate. What will be the good qualities of an ideal aggregate? These two will be enough for the next class because methods of determining the workability of concrete, we need to discuss this in bit detail, so it is time consuming. With this topic, we will also cover good qualities of an ideal aggregate in the next class. So till then, goodbye.